my title is actually, I didn't change the title from what has been assigned to me by Derek, that is to talk about, you know, policy making and the relation of science and modeling with policy making. I can't speak too much in general, however. I need to, how to say, to be humble and talk about what has been my experience in policymaking in the context of public health, and actually in a way that is more limited in the case of infectious disease burden, that unfortunately in the last few years, however, has been a very big event. Why I think, however, public health is a kind of prototypical example, because if we think about all these challenges that we have, you know, demographic crisis, migrations, diseases, climate change, biodiversity, urban development, all that at the end has the grounding point into public health, into our health. All those the things which are dysfunctional in those areas and all the challenges are going to land on our health, and we need to find way to address those problems. And you know, the point was indeed to use new digital data, new technologies, modeling, forecasting to address those problems. And what is the how to say the journey from science to policy? Well, is that we start with data, and then we have tools which could be mathematical, could be computational, could be just how to say even just very rough models. But then we have to transform and extract knowledge that at the end is actionable. This is the relation with policy. And this is what, in some cases, we forget by doing science, because we get so much in love with what we do that we lose sight of the fact that at the end, the policymakers need to have clear answers, need to have things which are actionable. And this was one of the problems. So how we go from science to actionable science and then to policies. Well, during the pandemic, for sure, for instance, we had what I call a policy intelligence disconnect. If you think about what happens in the first few months of the pandemic, we were always telling, you know, look, we have models. We know what's going to happen in 3 weeks, 4 weeks. We don't have a complete picture. And then we will talk about uncertainties, but things are going to be bad. And actually, there was no communication. So there was a lot of skepticism. There was a lot of let's wait. I try to list here, you know, some kind of general failure. So first of all, past history-based thinking, and so not to look at modeling or science, but to look more at what happened in previous cases. The fact that in many cases policymakers have troubles in acting under uncertainty, under situation in which you don't have clear knowledge. And then there is another part that is what I call the hubris, the fact that in many cases you think that you have solved the problem, even if people is telling, no. This is the classic case when we were telling, look, you don't observe cases, you have close traffic with China, but the epidemic is already here, is in the cryptic stage, and the people were very, very skeptical about that. I also report a sentence from one of the crisis room in which I was, you know, that was always told to me, and this is just actually to tell that policymakers have their difficulties too, that is, decisions should be based on things that actually happen, not the results of some mathematical equations. This has been told in different ways by different people, but not in a way that was aggressive or not believing to the modelers, but to the fact that, you know, there is a jump. You need to do an intellectual jump to really understand and trust mathematics or computational models rather than what's happening on the ground. Obviously, this is the wrong way of thinking, because, you know, in many cases, if you wait to to take actions is too late, generally. And the other thing is that in many other cases, we act upon mathematical knowledge. For instance, weather forecast. The only issue with weather forecast is the only issue. What is good with weather forecast is that you have something tangible. Even the policymakers has a photo from a satellite that shows the hurricane. When we talk instead about pandemics or other issues related to policies and modeling, we have plots, maps, mathematics, model, curves. Is different. Is different. In the decision room, it has a different effect. The other thing, as I was saying, is that there is a lot of issue with uncertainty. And this is, again, is something that from time to time might be surprising because it's, how to say, again, for weather forecast, we are very used to uncertainty. Look, these are two models. One is the European model, and the other one is the American model. This is European, and this is the US model for weather. And you see, this is, I think it was January 2022. It was a big blizzard hitting the East Coast. You see, both models are telling you something that is quite correct. There would be a blizzard. But, and you see, for instance, that this is the wonderful weather of the Boston area. We had, 20 inches of snow. This other model is 20 inches of snow. But then if you look at the New York area, one model is 20 inches and another model is less than 1 inch. Now, what do you do if you are the mayor of New York City? Do you close the city, you close the schools, or you keep it open? Well, actually, no one works like that with weather forecast, but actually you combine models together. And this is because models are not oracles. And this is something that has been, I think, misconstrued and miscommunicated during the entire pandemic. And I think it's one still of the major hurdles in communications with policymakers. We have still people who are going there and say, this is my model, this is my view of the future, this is what I'm predicting. No, it's not like that. And this is like for weather forecast, like for hurricanes here, where you see all these spaghetti are each one a different model. And you don't communicate a single model, but actually what you communicate is an ensemble of model, and then you do ensemble prediction. And then you have a cone of uncertainty that is the results of the sum of all the models plus their uncertainties. And you see here on this side, this is the different curves for pandemic projection that we had. This, I think, is the alpha wave. And you do the same. If you look at the different spaghetti, they seem crazy, but actually when you ensemble, you get something that is actionable. And this is the problem because, ensemble mathematics, the fact that you use more model to generate a consensus is actually not just mathematics, it's also communication. You don't have people going, this is my reality, this is my view, this is what I'm predicting. You have a very well poised communication with uncertainty. And this is what we should always try to do. And unfortunately, this has not happened. And we are going into these pitfalls over and over again. This is what we did with the Center for Disease Control. At a certain point, we decided we are not going to have single models telling what's going to happen. But you see, we have those, a lot of models and then aggregated in ensemble approaches. This is for the short-term forecast as well as for the long-term scenarios. And I don't want to get here into the nuances of it, but you know that those things are very different. Short-term forecast you can do under status quo assumptions and what is the situation on the ground, up to 3 weeks, 4 weeks at the most. Scenarios are different things that depends on the assumption that you do on the future and are not supposed to be actually capturing what will happen exactly in the future, but just to envelope what's happening, and is actually really directed to the policymakers to test policies. This is also something else that is generally badly communicated. Now let me open a parenthesis here. How we work in this area? Well, you see, this is again is the scientific interchange that we have among us in these different talks, in which it seems that we are jumping from one place to another. But actually, you know, Peter talks was talking about Brownian motion, diffusion, and actually the substrate that we use for modeling infectious diseases is reaction diffusion systems. Well, basically, you have particles that at this point are individuals, which are labeled by different states that represent the natural history of the disease, with the clinical, where all the transition and reaction rate are given by the clinical data that you get on the ground. And then you have subpopulations. So basically, patches in the geographical space that can change. It can be a census tract, a very small census tract, or a major urban area, depending the question that you are trying to address. And then you have individuals diffusing across those geographies. Well, the diffusion, however, is slightly different from what Peter was showing. It's a diffusion that is driven by data. And here it has to be very clear. We are not assuming anything on the diffusion process. We are just using actual data. So for instance, the entire airline data, including stopover, flight capacity, ticketing, et cetera, and the human mobility that comes from instance, from mobile devices and other sources. So what we do, in a sense, is this approach that we did start to build 15 years ago and more at this point, in which you see we have a tessellation of the world, in which all these places are small urban areas. And then we have a layer of networks. So first of all, we have the layer that defines the population. So how many people are there, gender, age structure, et cetera. But then we have different networks of mobility. We have obviously infrastructure, capacity, and so on and so forth. And what we generate are large simulations of how to say, business as usual or non-business as usual by integrating interventions and policies. This is basically the resolution that we have at the moment. You see that each of these subpopulation then is as a final resolution up to 20 by 20 kilometers, 20 by 25 by 25. We have also other layers that I'm not want to talk here. For instance, vector-borne diseases needs also layers that specify the abundance of the vector, for instance, mosquitoes, economic indicators, and so on and so forth. What is the final results of all that? This is, you see one simulation of this system. And you see each one of those white dots. This is an hypothetical epidemic that starts in Boston. You see each one of these individuals is a carrier of the disease. So somebody who is in a latent stage of the disease with no symptoms and can travel and go to other places and see the epidemic in those places. So this is what we do at this point. This is the capacity that we have to follow the single individual on this network. Well, here is, you are all scientists and you are telling me, Alex, this is cheating. You know very well that this is not working. Indeed, it doesn't work one single realization, because a single realization is obviously just one of the infinite possible trajectory of the epidemic that depends on the stochasticity of the transmission process, the stochasticity of the travel process, and so on and so forth. Well, what we have to do is to generate hundreds of thousands of those realizations and extract the statistical patterns that emerges because of the origin of the disease, the flow of mobility, and other characteristics. Well, that means also that each model has to be calibrated. And here, please, in many cases, I get the question, well, but you are then working with 20,000 parameters. No, these models have 2 or 3 parameters at the most, 4, and they generally are related to the disease, the transmissibility, and things like that. All the rest is data. The issue is that even for the clinical parameter, as you see here, we have parameter uncertainties. Nobody from the clinical side will tell me that the incubation time is exactly 1.5 days. I have distributions. And so I have to explore those distributions, those uncertainties. and generate many, many possible trajectories. I then compare those trajectories with the actual data. Generally, we use approximate Bayesian computation because numerically is convenient, but you can use many other techniques. And at the end, what we get is an envelope, for the possible trajectory around the data. Also to consider that the data are never exact. The ground truth in infectious disease epidemiology is very noisy because there is underreporting, et cetera, et cetera. And then on this trajectory, we can project the future, we can do scenarios, and so on and so forth. This brings us again to collaboration and large-scale collaboration, because a simple model, even at the global scale, can take 1.5 minutes to run on a top of the scale CPU. But if I introduce all the data that I need, all the mobility data in real time, et cetera, simulation can last for 1.5 hours. And now we have to generate basically every 2 days, hundreds of thousands of those simulations. This can be done in generating a gigabyte of data because you go down to those resolutions. So the only way to do that is to use high performance computing. What we did is, in these cases, is embarrassingly parallel approaches. So we were spinning 20,000, between 10,000 to 20,000 virtual machines with several threads and processors, so that you can generate in a few hours 100,000 simulation. In a half a day, you can run a campaign of analysis. This is all thanks to, and this is why it's not that I'm making advertisement, Google was giving us access to the full Google Cloud. And so that's why we are very thankful to them. Well, so this is a little bit the kind of infrastructure that has to be put in motion. But I want to tell you something else. I want to hope that the science, we have all different judgment of what has been done during the pandemic. Some people are completely, crazy about it and say that everything was wrong. Others say that everything was good, but the people were wrong. So, all these kind of things. But whatever you think, what we need to focus is how to do anyway better the next time. And the hope is that science can still drive policies. And I want to tell you something that is very recent. It's work that we have done actually in the last couple of years, but now we can discuss. And this is, by chance, is just going to be published tomorrow in Nature Medicine. And this is a new way, for instance, of monitoring epidemics. So one of the things when a pandemic starts is that we are always very late in detecting the signals and understanding where it is, where it goes, is already in the country or not, et cetera, et cetera. And so the idea here is to change paradigm, and instead of doing border control or testing people with swab, et cetera, we look at the bathroom of airplanes. So we just take wastewater from aircraft, and we do metagenomic analysis and other approaches that can be decided with authorities to do broad spectrum testing of the wastewater. And now the issue is how we can do that. So you have to set up thousands of airports, thousands of flights. Well, actually, this is where modeling comes handy, because what we have is our infrastructure, and we can simulate that process to a very high level of realism. Well, you need a lot of data that I don't want to get into the details, like what is the probability that you go to the bathroom if you are on a long-haul flight? Do you know that? Yes, actually, we know that. Also, that the difference if you go number 1 or number 2. So what is the probability that you spit in the bathroom, et cetera, et cetera. All that is collected. Then there are all the sensitivity of tests that we can use. And for instance, what we can measure through simulation is, if I have an outbreak in any place or in the world, what is the time to first detection that I have? Well, you see, this is the good thing, so that you can really measure that. And the time to first detection in many places becomes lower than 3 weeks. And so basically, you see, There are a few blind spots like Central Africa, and we can improve. And you know how many sentinels do we have here? Just 20. So with 20 sentinels and sampling only 1/3 of the aircraft through one place that is called triturator, so we don't look at single aircraft, but we look at aggregate wastewater, we can generally detect a signal in quite a short time. And what is important is, what is the short time? The short time changes with respect to the doubling time of the disease and other things. But basically what we have, if I can show that, is that, you know, we detect when you had basically between 20 to 40 diffusion events on the network. And this is a very small number because not every diffusion event corresponds to a different place, and not every diffusion event starts a chain of transmission. So you are talking with about a handful of chain of transmissions. And so this is also the other things that you can show is that you can introduce optimization approaches. For instance, if you want to detect a signal from Africa, you have to choose different set of sentinels. So you can use adaptive approaches. And you know, you have marginal return in the sense that after 20 to 30 sentinels, basically is like if you have the same performance like if you test across all the airports in the world. And this is because of the high heterogeneous nature of the airline network. We can do much more, also triangulate the signal and find where it comes from the pathogen, what is the possible transmissibility of the pathogen. This is by, how to say, you can imagine you have those systems, is like a radar, you know, you get a signal here, a signal there, a signal there, and then after a few hits, you can triangulate and get all this information. Well, just to give you an idea, this is something that in the US we are trying to build for real with the Traveling Genomics Surveillance Program, with the European Union, with other airports. And if we do some counterfactual, for instance, for some variants for which we have genomic data, like the B117, we see that we would have detection almost 2 months before what actually happened in the real situation. So this is something that really we hope that we can get this to a different scale. But this is the last part that goes back again to the future ICT things. These kind of approaches, this relation with the policymaking cannot be done with the usual academic model. That is the single teamwork, the competition, the elite journals, everybody keeping the data until it publishes a Nature and so on and so forth. We really need to go into a different approach that is coordination, is collaboration, is dependability, because you have to maintain those infrastructure. You have best practices. You need to share data nationally and internationally. This happens only with different incentives, like large-scale initiatives, which are backed up by governments, which are backed up by the international community, and bring us all together with a different perspective than just our, how to say, little shop, academic shop. This is something that we were able to, how to say, to take off in the United States. I hope it will go forward. There is really an effort to generate infectious disease national forecasting system. There are 10 centers across the nation. I'm working, coordinating the Northeast Center. I hope that this is something that will happen also in Europe. Although, as we know, the relation with politics, policymaking and science is getting more and more difficult the more time goes by. So, but, you know, I want to be optimistic and think that the next time we will be in a very different situation. Thank you very much.